And welcome to the YouTube channel D Creations Resources. We are looking at different concepts, and today let us discuss a concept from digital electronics. The name of the concept is pulse waveforms. So what are pulse waveforms? Now these are electronic signals that switch between two levels. One is high and the other is low, or you can say one is on and other is off for defined periods. So you can also say that they are the building blocks of digital electronics or timing circuits, communication systems, etc. Now there are going to be some key characteristics of these waveforms, and these characteristics are, of course, first one, the amplitude, the voltage or the current difference between the high and low levels. Then there is pulse width, which is sometimes denoted as by tau, and this is the time duration the signal stays at the high level during one cycle. Third characteristic is period, which is usually denoted by capital T, and it is the total time for one complete on then off cycle. The fourth characteristic is duty cycle, which is sometimes denoted by capital D. It is the fraction of the period that the pulse is high. So now it is going to be related to the two earlier characteristics that we spoke about, namely the pulse width and period. And how will it be related? If you recall, pulse width is the time duration the signal stays at the high level during one cycle, and period is the total time for one complete on then off cycle. So when you say duty cycle is the fraction of the period that the pulse is high, it is going to be given by pulse width divided by period and into 100% when you are talking about percentage. So you can say duty cycle D is equal to pulse width tau into 100 divided by period T. Now if the period T is twice that of pulse width tau, that means D is going to be 1 upon 2 into 100, that means 50%. This is a square wave. And then there is also rise time and fall time. This corresponds to the transition times for the leading edges in real signals, that means going from low to high, and trailing edges in real signal, which is going from high to low. And the pulses can also be called positive or negative. So when do you say it's a positive pulse? When it is rising from low to high and then returning to low. And the pulse is negative when it is dropping from high to low and then returns to high. So each edge has a leading and trailing designation depending on what direction it has. And the pulses can be periodic as well as aperiodic. So when you say periodic pulses, they repeat identically every t seconds. If you recall, t is the period. And they are useful for, say, LED blinkers or clock signals, etc. While the aperiodic pulses occur irregularly or on demand. So they are non-repeating. And for example, in keypad inputs, you may require them. Now, periodic pulses or periodic pulse trains are the basis for digital clocks, right? So aperiodic pulses will correspond to triggers in measurement and control. Now you would ask, what are some common examples of pulse waveform? So square wave, as we spoke earlier, duty cycle is 50%. For rectangular wave, the duty cycle could vary. So to think in simple terms, it's like blinking flashlight, right? So the flashlight is turning on and off in a steady beat. When the light is on, that's a high pulse. When it's off, that's a low pulse. Or the traffic lights which are switching colors after a certain time. Or beeps in video games or timers. Now these pulse waveforms are very important in digital electronics because all the digital gadgets like your phone or your computer, etc., they talk in a simple language of on and off, 1 and 0. So a pulse waveform is just a very fast on then off kind of a signal. So by sending a sequence of these pulses, circuits can represent numbers, letters, pictures, and sounds. So pulses are the clock beat, so as to say. So if you imagine a marching band, every musician needs the same steady beat to stay in sync. Now in digital electronics, a special pulse train called the clock signal tells all the parts when to start, when to stop, when to read data or move on to the next step. So without that regular pulse, the parts would get out of step like musicians trying to play without a drummer. So when you press a key on a keyboard or if you click a mouse, your computer is sending those instructions in a stream of pulses over wires. So for example, a short pulse can mean the letter A, or two pulses in a row might mean the letter B, and so on and so forth. So pulses let circuits package and carry information one bit at a time, like beads which are sliding along an abacus. You must have seen an abacus. So pulse waveforms act like traffic lights inside electronics. So they switch power on to turn motors or LEDs on, and they switch power off to stop things safely. By changing how long the pulse stays on, or its width, or how fast the pulses come, the circuit can control brightness, speed, volume, etc. But of course, you have to keep in mind that an ideal pulse will be a crisp pulse waveform where it will be clear high and clear low level. In reality, the electronic signals can be noisy or wobbly and they may not show this ideal kind of a behavior. So these are some basic aspects of pulse waveform. So now whenever you listen to the ticking of a digital watch, or if you see blink patterns on a night light, or if you hear the beep beep timing in microwave ovens, you should think of pulse waveforms, because all these rely on precise pulses to keep time, to send commands, or to control devices. Or if you want to say it poetically, pulse waveforms are the hidden rhythm that makes all the gadgets work together in perfect harmony.